We live in a world that demands constant progress. Everything needs to be lighter, faster, and more efficient than ever before. But this pursuit of innovation comes at a cost. Rising CO2 emissions and increasing noise pollution are shaping the world we live in, impacting both our environment and our quality of life. My name is Vanessa Cool and I'm a mechanical engineer from KU Leuven University. And in my PhD, I developed novel, lightweight structures that pave the way for a more sustainable and quieter society without compromising performance. Nowadays, modern dynamical systems like vehicles and airplanes must meet strict regulation and conflicting demands. They require robustness and reliability while remaining lightweight for sustainability and optimized for noise reduction to tackle noise pollution. Despite decades of research, balancing these conflicting demands remains an unsolved problem. The most promising concepts to date are sandwich panels and metamaterials. Sandwich panels consist of two outer plates with a core in between, strategically placed to maximize stiffness while minimizing weight. Meanwhile, metamaterials are engineered periodic structures that achieve remarkable acoustic performance by introducing band gaps, regions where vibrations are blocked. For the first time, this research introduces a solution that balances all three conflicting requirements through the fusion of sandwich panel and metamaterials, creating what we call sandwich metastructures. To unlock the full potential of these novel structures, this work presents a comprehensive framework for their analysis and design on three levels. Their characterization is investigated with a novel wave mode decomposition technique, the calculation cost is reduced with model order reduction, and an automated computational design framework is developed and validated. Before designing the sandwich metastructures, an in-depth investigation of their underlying physics was crucial. To do this, we must first understand how periodic structures are currently modeled. The design of periodic media is often achieved with unit cell modeling, which works as follows. In a periodic structure, the smallest non-repetitive part is selected and this is called the unit cell. The entire periodic structure is now represented solely by this unit cell. The unit cell is discretized with the finite element technique and infinite periodicity is applied using specialized boundary conditions. To evaluate how well periodic structures perform, two key performance indicators are commonly used. Firstly, dispersion curves show the relation between frequency and wave number. In these graphs, each point represents a mode of vibration propagating through the structure. Secondly, the acoustic performance is analyzed with the sound transmission loss, which shows the amount of energy that is transmitted through the structure in function of frequency. Although these performance matrices are well understood separately, their relationship remains unclear, limiting our ability to fully grasp how complex periodic structures behave. My research bridges this critical knowledge gap by introducing a novel wave mode contribution methodology. For the first time, the method directly links wave propagation and the acoustic transmission loss. This is achieved by expressing the sound transmission loss as a sum of different contributions, each corresponding to a specific wave mode from the dispersion curves. The novel methodology introduces a color coding of the dispersion curves, allowing us to visually track how each mode contributes to the sound transmission at different frequencies. As such, with the proposed technique, we gain new insight into the structural and acoustic phenomena governing periodic structures, offering a completely new and improved method for analyzing their complex behavior. Applying this methodology to a simple sandwich metastructure with two plates connected by a mass spring system reveals that both the structural and the acoustic properties of the core must be considered, since the path of least resistance ultimately determines the transmission. This observation highlights the necessity of vibro-acoustic coupled simulations and optimization techniques for our sandwich metastructures. These, however, come with a high computational cost. Since the dispersion curve calculation is computationally demanding due to iterative eigenvalue computations, this research accelerates them using model order reduction techniques. Model order reduction transforms complicated systems into simplified representations which are easier to compute while maintaining the important dynamical information of the original system. In our case, reduction is applied on the unit cell. Two methods are investigated. the block mode synthesis, which reduces only the interior information, and the generalized block mode synthesis, which further reduces the boundary part. Applying these reduction methods to a periodic case study reveals the critical role of unit cell selection. An inefficient unit cell configuration can hinder the effectiveness of the reduction techniques, while a small shift in its definition can lead to significant computational savings. The study underscores the importance of minimizing the amount of boundary information to fully exploit the potential of the reduction techniques. Both reduction methods are further extended to inherent vibro-acoustic metamaterial designs. The investigated designs now incorporate both a structural and an acoustic part. This required the development of a novel reduction basis that combines coupled and uncoupled mode information. Applying the developed methods leads to a large reduction of the computation time while keeping the error within an acceptable 2 order of magnitude range. With these advancements, the dispersion curves, once computationally demanding, can now be obtained almost instantly. The final part of the PhD focused on designing optimized sandwich metastructures. To enable an automated trade-off amongst the 3 conflicting requirements, a vibro-acoustic topology optimization framework is developed. In topology optimization, we start from a solid block of material, which is discretized into small elements. Each element can vary between 0 and 1, enabling topological changes in the design domain. In this research, the core of a sandwich panel is designed. Starting from a randomly distributed core, the optimization algorithm determines the optimal configuration, represented by clearly defined 0 and 1 elements. For the first time, our algorithm simultaneously optimizes stiffness, weight, and acoustic performance, automating what was previously an impossible trade-off. The objective of our framework is to maximize the sound transmission loss, while constraining the core strength and volume usage. During the optimization, it is again crucial to consider both the structural and the acoustic part, as well as the vibro-acoustic coupling. Running the optimization on the case study reveals that the initial iterations focused primarily on the volume usage, followed by a substantial acoustic performance gain, achieved through dynamic behavior exploitation within the core. The optimized sandwich metastructures utilize a novel mode coupling effect, where bending at the bottom is converted into translation at the top, resulting in an extraordinary wave attenuation effect that was previously unexplored. However, to confirm this novel phenomenon, experimental validation was essential. Using a new methodology, we developed a simplified experimental setup with purely structural excitations and measurements to estimate the 2D sound transmission loss on a near 2D sample. Only frequency response functions are measured and combined in post-processing to assess the acoustic performance of the investigated design. The experimental results confirm an excellent match with the numerical predictions, validating the superior acoustic performance of the optimized design. This shows that the developed methodology is not just theoretical but holds real-world potential. In conclusion, this manuscript demonstrates the potential of novel sandwich metastructures as lightweight, strong, and highly effective acoustic solutions. This is achieved through a comprehensive computational framework covering analysis, design, and experimental validation. 3 fundamental contributions are presented. Firstly, a novel characterization methodology is proposed. Secondly, the dispersion curve calculation is accelerated, and a vibro-acoustic topology optimization is developed and validated. This research as such fundamentally advances the field of metamaterials, topology optimization, and model reduction, pioneering a new class of sandwich metastructures that unlock lighter, stronger, and quieter designs. These advancements lay the foundation for a future where sustainability, silence, and high performance go hand in hand. For more details, find the complete manuscript at the following link.